In this video, we'll look at solving our reactor mass balances by introducing a problem and simulating it and getting numbers out and seeing whether they make sense to us. And we'll do that for equimolar and non-equimolar reactions and for the three ideal types of reactors, namely batch, CSTR, and PFR. Now, in most simulation exercises, something I observe quite frequently with students is there's a tendency to just jump in and start writing the code. And of course, that's going to result in several errors if we don't take the time to formulate the problem first and clarify for ourselves what equations it is we're trying to solve. So let's switch over to this view where we'll just develop our mass balances first. So just starting from first principles and reintroducing the basic mass balance, we can write ddt for the number of moles of component I in the reactor. That must equal the molar flow rate into the reactor of component I minus the molar flow rate out of that reactor plus the rate of formation of component I. And of course, we have to add up the contributions to the rate from all parts of that reactor, so from all sub-volumes within that reactor. So here, of course, we are talking about some arbitrary reactor which is fed by some streams in, and we've got streams withdrawing here, and we can partition this reactor into as many sub-volumes as we like. And so if we are considering some volume dV, then within the sub-volume there exists some reaction rate Ri, some rate of formation of component I that's local there. And then if we add up all those local rates of formation, then we'll get this overall rate of reaction. And then we've got feeds in and exit streams, and that results in an overall rate of change of component I. So starting with the batch case, if we take the idealized batch reactor, which means that it's perfectly mixed, which we symbolize with that stirrer in there, then this equation can be simplified because we can neglect these flow terms. And so we can write ddt ni equals, and then just this term survives. And because it's perfectly mixed, that means the concentration is the same everywhere and the temperature is the same everywhere. So the reaction rate must then be the same everywhere. So we can say the overall reaction rate must simply be Ri times V, the total volume of that reactor. Then of course we can rewrite the number of moles of component I as the concentration of I multiplied with the volume. And let's say we are doing this for the following reaction. So let's say it's a simple A being converted to B reaction. So we can write here ddt of Na, so doing a balance on component A, and we can write the number of moles as the concentration of A multiplied with the volume of reaction. And let's say this is an elementary reaction. So let's say it's a first order reaction with K being the reaction rate constant. Then we can say that Ra equals, and in this reaction A is being consumed, so it's the reverse of a rate of formation. So we have to write this as a minus Kca. Right, so we can replace this Ra here with a minus Kca, and we've got the volume here. So assuming for now that the volume is a constant, we can remove that as a constant from this differentiation, and the volumes can cancel, leaving us just with ddt of Ca being equal to minus Kca. Excuse me. So we've got this basic equation, and of course to solve this we'll need the initial condition as well. So we can say that for this reactor, there must have been some concentration of A initially. So we can simply define that as a Ca naught. So we can say Ca at T equals naught equals a Ca naught. And of course, in our batch system, we are going to charge this reactor with some reactant initially. So there will be some non-zero initial A concentration in there. And then if we integrate this balance, if we integrate this equation with this initial condition, of course, the solution is simply Ca equals Ca naught exp of minus kT. So this is our concentration as it varies with time. So of course, in this case, we have this nice, easy analytical solution because this was a very easy equation. So we would still like to establish some numbers around this. So let's just simulate this equation and get a sense for how concentration is changing with time. And then let's look at some numerical ways of solving such equations as well. So to do that, we're going to use MatLab. And you can find MatLab normally with this kind of icon, and I've opened it here already. And something to notice is that MatLab will normally default to this type of directory. And of course, we need to switch to where we want to store our MatLab files. So I've prepared a folder here. So you can see in my case, the folder is in this directory. So what I normally do to copy long directory names like this is to just navigate using Explorer and then copy the text for that from the address bar here. So I'm hitting Control C, and in the command window we'll use the change directory command, and then pasting in the path there, I can switch over to that. So you can see my path has changed to that now. So we are going to create a MATLAB file, a script file, which will have our program statements. So we need to be in the right folder for that, or the MATLAB compiler is not going to be able to find our code. So we've chosen this is where we're going to work. Of course, if you have spaces in your folder names, if you have some spaces in there, then what you have to do is write that in as a string. So you have to specify that what's coming in is a string, and then you can entertain spaces if you have spaces in your folder name. So that's how you change to the right folder. And I don't use the built-in editor in MATLAB. You see, if you type edit, you'll get an editor. I tend to use a different editor for all my coding work. So I tend to use the Sublime Text editor, and you can download that if you just do a search for Sublime Text. So let's create our code here. So let's create a new file and save this in the folder. So let's call this simulation 1, so SO1, and we need a .m extension. So that's an empty file, and then I'm going to say here as an initializer, close all, clear all CLC. So close all will close any figures that any plots that we have from, let's say, a previous run. Clear all will clear all the variables in memory, and CLC will clear the command window of any statements. Right, so that's just an initializer, and let's now simulate this equation that we've written out here. So you can see, of course, we have to specify Ca naught, our initial concentration. So let's say Ca naught equals 20, and of course I'll assume SI units for everything, so we're going to say moles per cubic meter. And we need to specify also the kinetic rate constant. So let's say we choose arbitrarily 3e minus 4. And this is going to have units of per second. We'll talk about that a little bit just now. And now we would like to view the concentration for a series of times. Okay, let's not say that just yet. Let's just calculate the concentration at one instant in time. So let's just stick in our equation. So Ca is Ca naught multiplied with exp of minus kT, and that's k times t. And so let's specify a time here. So let's say we wanted to know the value of the concentration after half an hour of operation. So let's say 30 times 60 minutes, 30 times 60 seconds per minute. And if we want to view the result on the screen, then we could simply omit the semicolon there. So if you don't include a semicolon, then when you run this in the command window, it will give you that output to the screen. So let's just do that. Of course, in your editor, you'll get some indication that your document is not yet saved. So you hit Control S to save that, and then Alt Tab into your MATLAB command window, and we want to type in the name of that script file. So we'd named it SO1. So if you run that, you see that the concentration has approximately halved, and so that's the result that we get for half an hour of operation. So now, of course, what we'd normally like to do is view the concentration as it varies with time. So we would prefer to use a series of values for time instead of just that one instant. And there's a handy function in MATLAB to do that. So that's the linspace command. So linspace, as the name implies, gives you a set of linearly spaced values. And the first argument is the starting value in your series. The second argument is the end value. And the third argument is the number of points you are going to use to get there. So let's say we'll use 50 points. And I'll often use variables just to help make that readable. Because if you look at it like this, you can't immediately tell what the 60 and 50 is supposed to be. So it's useful to state here T naught is 0, Tn for end is 60, and Tz, my convention is to use a Z for number of points. So here we can say T naught, Tn, and Tz. So you can say that's slightly more readable. And let's look at the result of that. So of course we don't need this one anymore. We no longer want a single value. We now want a series of values. So let's take off the semicolon and see what we have. So if it's SO1, you can see now T is a series of numbers that starts from 0 and ends at 60. And we have, you can see here it's saying columns 1 through 13, 14 to 26, and then up to 50. So we've got 50 values here. We've got 50 points going from 0 to 60. So that's what we wanted, right? We wanted 50 points going from 0 to 60, and we specified that should be linearly spaced. You can also logarithmically space those points if you just use log space instead, but we'll stick to linspace for now. You can see also that we have a result down here that Ca is given to us over 50 points as well. So if the T that we put in here is a vector of values, then we'll get a result which is also a vector of values if there's no other vector operation. I mean, if k was also a vector, then that product would of course be a scalar. But here it's a scalar multiplied with a vector, which is of course a vector, and that's another scalar. So that result is a vector, and then that vector multiplied with that scalar gives you a vector of values. So we've got concentration as a function of time, and if we look at the numbers, you can see that it's got that initial condition that we specified. So we had specified an initial value of 20, and that 20 was used in this expression. So it started at 20, and then that value dropped over time, and but it hasn't dropped very far. It's a very slight decrease. That seems to be at odds with what we had earlier when we said that it was half an hour of operation that we wanted. So here we've specified the end time is 60, which is just 1 minute. So let's increase that. Let's say it's 60 times 60. So we want actually 1 hour of operation now. And we'll get a different result if we run this then. So again, your workflow should be, you'll edit your statements and then you hit Control S to save them, Alt Tab into your command window, and then hit the up arrow. So if you hit the up arrow, that brings up your last command, and then you just hit enter. So you see, if you do it that way, you become very fast at editing and going back to getting a result. Anyway, that's just by the by. So we've now increased the time to go to 1 hour of operation, and you can see the concentration has dropped much more significantly now. So it's gone from 20 all the way down to 6.8. Now that's all fine. We have the numbers, but of course it would be better to visualize this. So to do that, we can simply plot these two variables. So we can say here plot t comma ca, and we can specify what type of line we want plotted. Let's just leave it like this for now. So again, Control S to save, Alt Tab into the window, up arrow, enter, and you see we've got a result here. Now there are a couple of things that we can improve here. Number one, we should be labeling our axes. So let's do that here. So to create a label on the x-axis, it's x label, and then open up a string and say here time t, and that has units of seconds. And let's label the y-axis, y label, concentration Ca, and that's moles per cubic meter. Right, now that's all fine, but there are some things we can do to improve this labeling. Let's just see first what it's going to give us. So Control S, Alt Tab, up arrow, enter, and you can see it's labeled now. But what's not quite ideal for us is that we'd like this 3 to be superscripted, and we'd like this A to be subscripted. So if you go in here and if you use, in this label, if you use an underscore, then when MATLAB passes the string, it will detect that you've used this underscore. By this, you must have meant that you want what follows to be a subscript. So it will use a subscript then, and here, if you use this this symbol, that up arrow, then it's going to detect that you wanted to indicate that that should be a superscript. In this case, we actually mean it to be raised to the power. So that's actually what we mean. But anyway, so Alt Tab, Control S, Alt Tab, up arrow, enter, and now you can see you've got superscripts and subscripts in there. So that's one. Another thing is we've got a continuous line plotted here, whereas we can see these are actually discrete values. So in any computational work, you will always generate a discrete set of numbers rather than a continuum. So we could change this to a set of points if we wanted to. So we can change that line style. And to do that, here in the plot statement, we can add a third argument, which will be the style of line that we want. So by default, it's on that dash. So the dash means use a continuous line. And of course we can change that to a double dash if we wanted a dashed line. We can change that to a dot if we want dots, and we can use an X if we want little crosses there. So here you can see crosses, and if we use dots instead, you can see we've got the discrete set of points there. Right, so that's a simple one. That's if we want to just plot out a series of points in MATLAB. We can, of course, plot multiple curves on the same set of axes. So let's say we wanted to plot component B that was forming as well. So in this relationship, we've got that that B forms as A is consumed. So we could write the mass balance that the concentration of B must equal the initial concentration of A minus the current concentration of A. So we had started out with a certain amount of A in that reactor, and then if we look at what we currently have, the difference between those two must be the number of moles that have been converted into component B. So we could say the current concentration of B must simply be the initial concentration minus the current concentration of A. And so we can include that in our equations list here. So we can say CB equals CA naught minus CA. And of course CA is a vector of values. So this is a scalar minus a vector of values. So the result is going to be a vector. So it's just going to repeat that scalar for each component of that vector. Now, to include this this curve, what we'll do is include a new triple here. So they call them triples in the plot command. So we can include T, CB, and let's use a different line style for that. Let's use X's there. So it's just a matter of adding more arguments to the plot statement. So we've got the first triple here, which is going to give us a series of values for the concentration in A. And now we've got a second triple here, which is giving us the same thing in B. We can see we'll possibly need to change our labeling here, but let's just see what we get first. So again, and I won't keep repeating this, Control S, Alt Tab, up arrow, Enter. Right, so you've got A and B over here. So your concentration of B is of course rising as A is declining. And now it's no longer appropriate to say everything on this set of axes is CA. So let's just take off the CA from there. So it's still just concentration, so we can leave the rest of it. But what we'll want to do now is distinguish between those two curves. So there's another useful statement, legend, and we can say component A and component B. Control S, Alt Tab, up arrow, Enter, and there you go. It's labeled now, and we've got on the set of axes all the information we need to understand the results we've got.